So we're now going to move deeper in the system to lower structural levels, think about melt production and extraction, the deep crust. I'm going to move to Ecuador, and I'll hand over to Hugo Dominguez.
Thank you very much for the introduction. So I would like to start looking at the big picture. So this is a sketch of what could be the cross section of a continental crust with a source at the bottom. And I think we can all kind of agree on what could be the big picture here. But there are still lots of questions if we look in details. For example, how do you form the melt? How is it extracted? How do you start to segregate it? And also, how does it migrate in the crust? And how is it then forming, for example, a pluton of a batholith? And then how we can contribute to a volcanic system. So one way to study that is for one modeling. That allows us to model things, because it's kind of tough to work on this kind of time scale and look at the deep crust. So in the metamorphic community, we love to do phase diagrams. So here it's a recent work from Kobling and Patterson in 2017, and they looked at modeling of migmatites, and they tried to look at different scenarios for what's happening if you fractionate the melt, what is happening with the leucosome, and water fluxing and all these kind of things. And so here you're looking at just a PT phase diagram where they're looking at different reactions and also mineral abundance of the rocks. And also, so this is more or less for the metamorphic community, and for the whole magmatic community is also interested in what's happening here. And so lots of effort have been done in trying to model this, what we call porosity wave, for example, of channel flows by Ludovic Resenthal in 2019. But so when we look at the bigger picture, it's quite tough to put all of this together. And so it's important to have some constraint with natural settings. And so I will not talk about Ivrea today, but I will bring you to Ecuador. So Ecuador is not Ecuador, El Oro Complex in Ecuador. So you have here the geological map of El Oro Complex. And what's interesting with this place is that if you kind of look here, you have here this pink formation, which is composed of migmatites. You have this orange formation here, which is amphibolytic, amphibofacious metapelites. And then you have a pluton here, which corresponds more or less to this. This is the scheme on the left, and we have the same color. And so if you look at the black line here, you have a gabbro at the bottom, and then blue schist metamorphism. So if we are looking a bit at this of the history of what happened here, we had typically a deep continental crust that was intruded by a gabbro at the bottom that provide a heat source that produced melting. So we have the formation of migmatites. Then the melt is extracted, and you form this pluton in close to the surface. And then we have a blue schist facies that comes here, so sediment that are at the bottom that quench the system. So we have a very short event, quite well constrained with no much deformation. So it's a good place to play with. So when there's this summer, I started sampling, and I'm still processing on the natural samples. So I will not show any data from that, but I will show what I've done in terms of modeling. So the idea was to come up with a simple model on the crustal scale to try to play with. So this is the idea. We have this is a 1D model. So here you have a pile of rocks, and we have interlayers of sediments, so pelites, semi-pelites, and sandstones over like 25 kilometers. We have the gabbro at the bottom. And so the idea is to define on each of these units pressure and a temperature. So the pressure we consider it's isobaric for the whole model. So we have the same pressure for over time. And then we solve the temperature equation like lots of people have done in the past. So just a 1D heat transfer equation. And now that we have a pressure and temperature, we can call thermodynamics. So we minimize Gibbs energy using Triassic domino. And then what we are really interested in here is the melt, what is happening with the melt. So we extract the water every time. So we don't consider water flux melting here. And we then extract the melt if we have more than 7 volume 1%. So this is the threshold we define. And we save it somewhere, and we will look here at the composition and the volume that is produced. And then we repeat the process for 10 million years, which is the metamorphic event we are considering. So this is the thermal model we are considering. So this is the depth versus temperature. We have the initial profile here, so we consider a classical thermal gradient, and we have the intrusion of our gabbro, which has 1,250 degrees. And what we have as constraint here, the PT estimates that were defined by Riel in 2016. And so we consider this is the peak temperature recorded by the rocks. So the idea is for our model is to pass through these points and the maximum temperature. So this is here the profile we come up with. So we have the cool down of the gabbro after 2.5 million years, and then the system cool down. So you see that the green line here is the maximum temperature reached by the model, which more or less corresponds to what we can have with the data constraint. So now that we have the pressure and temperature, we can look at the result of the model. So here you are looking at the task diagram. So you have alkaline versus silicon. So this is used to typically plot magmatic data. So the idea is that I will plot here the melt composition produced by the model at each time step. And on the right here, you have a column of rock in 1D. So it's similar, you have the 3 layers of sediments, but here you're looking at the silicon content. So you will expect that to decrease when I will run the model as the melt is extracted. And so if I run the model now, you can see that I'm producing here granites with more or less quite a constant composition over time. So the melting event is occurring for 3 million years. And you can also maybe notice here some different composition. And on the right here, you can see that, this is not running again. Yes, you can see here that the rocks are melting. So we are increasing the silicon content, and especially in 1 layers, which is the pellitic layers. And what you observe here is that you have a slightly different composition for this. It's basically because we are also making a slightly the quartzite and the semi-pellite, which has a slightly different composition. And you can also here notice the natural data from literature for the pluton we are interested in. And so what I also can observe is the volume produced. So basically here you are looking at the time versus melt thickness. So as I'm in 1D, this is like correspond to a thickness of melt we are extracting in each time step. And what is interesting here, the orange curve, which is the integrated cumulative melt thickness. So basically it means that at the end of my model, I've produced 2.5 kilometer of pluton, if you want. And this is here the geological map of the area we're interested in. So this will represent the magmatites have melted and then the pluton that is in place here. So yeah, so I've shown here a first order model, very simple, just with the thermodynamics to try to model the crust in this area of what happened. I would say the very simple thing that I've considered here is the melt extraction. So I've just considered a constant threshold, and then I'm teleporting the melt. In the future, what I'm interested in is to complexize this a bit and to combine this with what we call it phase flow. So I've written this 2D code to model magma ascent. And so the idea would be to then combine that with the thermodynamics to come up with a bit more complex model to see what we can get from that. Thank you for your attention.
Lots of time for questions.
Yeah, so there was quite a difference between the model and the natural rocks. You think that's the natural rocks have started to fractionate a bit and you've lost really evolved melt from those?
Yeah, so here I'm quite good in silicon content, but yeah, I'm a bit off in alkaline. And yeah, that's my main hypothesis. I would say to fractionate it on the way. So you crystallize plagioclase, feldspar, and so you will decrease this. And that's what I would like to see with the more complex model, maybe. Yeah. Yes.
And what was the melt model that you used?
So I use database 6. So yeah, the latest model. I tried with database 5.2. The result was quite similar in this case.
I was just wondering what depth you emplaced the melt at in the model, and if you try varying that emplacement depth and
Yeah.
that change?
So here I'm not emplacing the melt.
Oh.
So yeah, so it's very simple. I'm just teleporting it. As it's a mass balance problem, I would say that yeah, what you take away is still in the sequence, so the pressure should be the same more or less at the bottom. But yeah, that will be interesting to put it up. Normally, you should not be able to. You will not melt when it will take in place. So that's not. Yeah. So that was interesting in melt. So it's okay to I guess.
I think you probably said this, but I missed it. Why were you cooling so rapidly from the base?
Mm-hmm. So you have basically a subduction that is bringing sediments at the bottom of the sequence, and so it's very cold, and so it's squishing the system very fast. Yeah, that's right.
So each time you extract melt, you shift the solidus to higher temperature.
So there is no feedback. There is no feedback with the melt now. We could introduce that quite easily. That's something I would like to try.
Do you think that would have a large effect on the results?
I'm not so sure. It should. So normally it's. So you mean how it impacts the solidus?
Each time you extract a parcel of melt from the sediment deep in the crust, presumably it becomes more refractory in the solidus.
Yes. So that should be taken into account because I'm updating the composition of the bulk rock. So that's already in there. Thank you.
Yeah, I probably missed, you showed a green curve that was the maximum temperature conditions that, yeah.
That is reached by the model. And so, yeah, I'm considering that this
And then
is,
it cools down.
yeah. So I consider that this is what the rock we call it.
So, and the thickness of the mafic complex, let's say, how much is it? 5 kilometers?
I think, yeah, it's 3 to 4 kilometers. But then it's hard to see on the plate because it was, there was then the blue sheet that came. And but here, yeah, we have 3 kilometers, I think, here. Yeah.
Basically, in theory, it should, the mafic, the magma cool while the rocks above are heating, and it doesn't until they get to the.
So you mean for the gabbro?
Yeah, the gabbro should crystallize while the camphor rocks are heating.
Yes. So here you see that the temperature is decreasing at the beginning, but we consider that there are a heat source for 2.5 million years. So we are still injecting gabbro at the bottom, so the heat source is still there, and then we cool down everything.
Nice.
That's the best hypothesis that's the best fitting that you obtain with this hypothesis.